All right, here we go. It's Don here with a Ham Radio 360 live demo. We'll see if it works. We'll see what happens. And this is just to show you what we're doing here in my ham shack with the Ham Radio 360 antenna analyzer. So this is the first time I've done anything like this. So anything's bound to happen. I'm sure it'll look horrible. It'll sound horrible, but we'll give it a go and we'll see. So first off, got the board. As you know, I built it, had a lot of fun doing that. It's been a great little project, really enjoyed it. And I took it upon myself to start delving into some of the software here and see if we couldn't do a few different things with the project and update the firmware, maybe make it do a few more things, and maybe build a framework that we could use to do some other things like the power analyzer and maybe some other things. So I just thought we'd give it a go and we'll see what happens. So one of the first things that I did was that I rewrote the Arduino code. And what I did is I took it apart and rewrote it as a class. And did a little bit of C++. And oh, lost my mouse. Here we go. Here's the mouse. And split out the components for the DDS, the analyzer, and then the actual code that does the job. So what I did is I wrote a DDS class that is called by the analyzer class that is then called by the state machine, which is the actual code. This would allow us later to replace the DDS with a different DDS, and none of the top level code would have to change. Everything would be encapsulated in the DDS class. So the DDS class is basically the same code that we had, only we just have an initializer, a start routine, and then basically it's the basic code that we had in the original project. That is then called by the analyzer class, which again is the basic code that we had in the previous project, only I've added the setters and getters for the various components, frequency start, frequency stop, the number of steps, that kind of thing, and then built the actual code. Now, one of the things that I did change is the way that we put the information back to the PC. What I did is I modified this code to feed the data back to us in JSON. Now once it comes back in JSON, we can then use some higher level routines to actually do the code. So basically again, same code that you saw it before. The only real difference is this real ugly sprintf that gives us our JSON back. And yeah, so that's that. I'll ship along the code if you're interested. And there. Then we have the main routine that gets called. And what I did is I built a state machine. So the state machine, based on whether it's getting the start frequency, the end frequency, whether we're going to start a scan, whether we're going to return a status report, or what we're going to do. So again, kind of looks the same. We have the basic setup for the liquid crystal. Here's where we declare our antenna analyzer class. That then calls down into the DDS class, instantiates it. Then if we go right to the bottom and look at our setup, same stuff. Set up the async interface, set up the display, but now when we go into our loop is really quite simple. We check to see if there's any serial data available. If there is, we process the incoming byte, and then we check. Are we in a scan? If we're in a scan, there may be, remember AA is our analyzer class. If there's more data and we have an active scan, we go and we get the data and we get it ready and we send it back. The serial print sends that back out to the caller, and what we'll see later is that caller is a Python routine, and that Python routine will then take it and feed it into some Python code that will then do the graphing. So basically it's the same, except now we have this process incoming byte. The processing incoming byte now, if it's a number, just like it was before, we add it to the current value, upping it so that we get a value. We then say if it's an A, it's a start. If it's a B, it's an end. If it's an N, that's our number of samples we're going to take. And then finally, a little farther up, we actually process it. So if it's a start, we set the start frequency. If it's an end, the end frequency. If it's a scan, we do the scan. And there's a little bit of housekeeping, a little bit of stuff. And there it goes. So I'll attach the source code along with this video so that you can take a look at it. But that then goes into a web-based application that is built with the Flask and Python toolkit. And right now there's just a basic page that shows what there is, and then we have a run sweep. The run sweep, just like before, we can put in a start frequency and an end frequency, and then the number of samples that we might want to take, and then we run a sweep. And there's our sweep, and there is our graph. So now what you see down here is the actual output of the Arduino. These are the JSON package. So we got the current frequency. There it is, the voltage standing wave, forward and reverse voltage. And then it all put together in a JSON package, and it turned over to the Python code. So the Python code gets a little messy because it is all built on a toolkit. The toolkit makes it kind of easy to do the web pages. It kind of obfuscates the actual code, but really all we do is we get the start, the stop, the samples, and then I've hard-coded the port. I haven't quite figured out how to get the port number in here yet. Open it up, send it. Remember, A was start, B was stop, number of samples, put it out. We then send the S character, which was the start of the scan, and loop, collect up the data, stuff it into JSON, and through the magic of Python we split it into some arrays. I could explain that, and then graph it. We'd get a line graph, add some labels to it, and render the template. And there it is. You've got a nice little web page that does some graphs. It's truly portable in that this will run on a PC, on Linux, and on the Mac, as you can see here. Changing a value will rerun the sweep. Now right now the thing is right in the into a dummy load, and you can see that it is spitting out the lowest minimum frequency and the standing wave ratio of 1.37 on the screen. and along with giving me the ability to print the graph. Now, a couple of things I haven't done yet is the buttons don't work in the way that they did before. I still got to implement that. I couldn't figure out what the mode button did. I don't think it really did anything, so I was thinking of using that potentially for some other functionality. The code is kind of icky because I've still been playing with it, but I thought maybe you guys would like to see what we've got here, and maybe we could use this for some other things, because while in the case of this particular project, having it as a web page and in this fashion, it might not be as useful. I got to thinking if we could build a little framework that would have some Arduino code, allow us to communicate in a clean fashion back to a server running Python, or if you wanted Node.js, you could then use that to stuff it in a database. At that point, for example, with the power analyzer board that you people are looking at, we could then average the power, the power statistics over time, record it, and potentially even with the antenna analyzer here, we could put it into a database so that you could record the characteristics of your antenna on a date, and then if you thought your antenna was performing differently, you could run it and be able to run a comparison against the information in the database. I just haven't done that. I was going to take a look at that in a little bit here. But I wasn't sure how useful this would be. I wasn't sure if anybody else might be interested in this. So I thought I'd give it a try and see what you guys all thought. Again, this is the first time I've done anything like this, so I'll load it up to YouTube and let you take a look. Take care. It's Don saying 73 for the Ham Radio 360 podcast and Antenna Analyzer project. Bye-bye.